Hello there. Discrete mathematics, the branch of mathematics that deals with distinct values rather than continuous ones. Sets, relations and functions, mathematical logic, cryptography, graph theory, counting theory, probability are few branches that fall into discrete maths. Our project is based on cryptography, which is the study of how to create security structures using concepts of number theory and modular arithmetic. Computer is a device that deals in data and information to carry out its task and to make sure that data does not fall into the hands of dangerous entities, which is the utility of cryptography itself. It uses mathematical concepts and algorithms to transform data into various forms so that it is hard to breach. Cryptography is widely used in daily life. For example, to send passwords to servers of different websites and storing them safely. The transmitted information is secured using cryptography. Now, let's have a flashback to the history of cryptography. The most former user of it were the Spartans to send messages during war using device known as skytail. Secondly was Julius Caesar, who invented a substitution cipher. In his cipher, all the characters of sentence being shifted by three places to create encrypted message. Different crypto systems are in existence for different purposes. RSA crypto system is used for data encryption and other digital transaction over the web, whereas ECC, that is elliptical curve cryptography, is widely used in cryptocurrency to provide ownership and to provide signatures in Apple's iMessage service. Now, let's have a talk on RSA crypto system. Say you want to send a message to your friend. The algorithm for RSA is as follows. First, choose two large prime numbers, say P and Q. Now, compute n equals to P times Q. Choose a number E not equal to 1 such that GCD of E and P minus 1 times Q minus 1 equals to 1. Compute D congruent to E inverse modulo P minus 1 times Q minus 1. Now publish E n and keep D as a secret. Here E and n are public keys. Then compute Y congruent to x raised to E modulo n. The receiver receives Y and reads it. Receiver then computes Z congruent to y raised to d modulo n. Read Z. This Z is equal to x. As you can see, this is rather straightforward algorithm but very effective. Let's have an example. Say Alice wants to send a message hi to Bob. First, select P and Q as 13 and 7 respectively. Therefore, your n is 91 and E is equal to 5. First, encrypt H, whose ASCII value is 72. Y congruent to 72 raised to 5 modulo 91 and y equals to 11, which we will eventually publish. Similarly, encryption of I, whose ASCII value is 73, takes place. Here y is equals to 73 raised to 5 modulo 91 and y is equals to 47, which will be published. Now the private key D congruent to 5 inverse modulo 72, which is equal to 29. It's time for decryption of H. Z1 is congruent to 11 raised to 29 modulo 91, which is equal to 72. Decryption of I is in similar fashion. Z2 is congruent to 47 raised to 29 modulo 91, which is equal to 73. Thus, the message is sent and received securely. First of all, let's take a brief look at elliptical curves. Why we chose elliptical curves? It is because elliptical curves use shorter encryption keys which further do not acquire larger memory and CPU resources. The elliptical curve is written as E is equal to xy such that y raised to 2 is equal to x cube plus ax plus b. Here A and B belongs to K, where K is either reals or rationals or complex or prime field element. There is condition that we must check, which is 4a cube plus 27b square should not be equal to 0. Now let's understand what our group operation is. First of all, let's take into consideration addition. P and Q are the two arbitrary points on the curve. The slope of line PQ, say M, is equals to y coordinate of P minus y coordinate of Q upon x coordinate of P minus x coordinate of Q. The x coordinate of R, where R is a point which is addition of P and Q, is equal to M square minus addition of x coordinate of P and Q, and y coordinate of R is equals to M times x coordinate of P minus x coordinate of R minus y coordinate of P. Another group operation is point doubling. If the point is added to itself, we say it's point doubling. Its slope would be 3 times xp square plus a. Here a is parameter of elliptical curve upon 2yp. xr is equals to m square minus 2xp and yr is equals to m times xp minus xr minus yp. Now, another group operation is adding vertical points. We know the addition rule and applying it here, that is adding the vertical points, we get p plus q a point at infinity. If x coordinate of p is equals to x coordinate of q, which is obvious. For the case when p is at curve's vertex, that is x coordinate of p is 0, then p plus p is equals to point at infinity. The scalar multiplication. Suppose we want to do multiplication q is equals to k times p, then we do repeated addition of p k times. We have the liberty to select any point on curve as generator G belongs to elliptical curve defined on finite field Zp, which generates a cyclic group. When we generate 2p, 3p, 4p from P, while after a while we will get a C such that Cp is equals to P, C plus 1p is equals to 2p, so on, and points P, 2p till C minus 1p form a cyclic group. Choosing G such that it generates larger cyclic group, that is more number of points, so that it would be hard to find private keys. The size of cyclic group is denoted as n equals to order of G, which is defined as smallest positive integer such that n times G is point at infinity. Now, the cofactor is defined as h, which is equal to number of points on the curve upon size of cyclic group. Ideally, h should be equal to 1. Elliptical curve discrete logarithmic problem. Suppose E is an elliptical curve over Zp and P belongs to elliptical curve defined over finite field Zp. Given a multiple Q of P, the elliptic curve discrete log problem is to find K belongs to Z such that Q is equals to K times P. Calculating K from given Q and P is time consuming and is considered to be impossible for big value of K. Now begins the main part, the elliptical curve cryptography. The algebraic structure of elliptic curves over finite fields is the foundation of ECC. To provide a similar security system, elliptical curve cryptography requires a smaller key than non-elliptical curve cryptography encryption. An elliptic curve is a planar algebraic curve defined by an equation of the form y square equals to x cube plus ax plus b. When a straight line is drawn intersecting the curve, it intersects almost 3 points. The key property of this curve is that it is symmetric about x-axis. Here, P is equal to field that the curve is defined over. G is of course the generator point. A and B are values which is defined on the curve. H will be the cofactor, and M is prime order of G. Let's understand the aspects of Diffie-Hellman key exchange. Say Alice and Bob wants to interact on web. For that, let's say there are two public keys, namely P equals to 10 and G equals to 18. Alice has a private key A equals to 4 and Bob has a private key as B equals to 5. Now, Alice will compute X congruent to G raised to A modulo P, and simultaneously Bob will compute G raised to B modulo P, which is congruent to Y. Value of X will be 6 and value of Y will be 8. Y is sent to Alice and X is sent to Bob. They further simultaneously computes their K's. Ka will be Y raised to A modulo P and Kb is congruent to X raised to B modulo P. Of course, the value of Ka and Kb is same, hence the secret is shared. We have elliptic curve and its public keys. Alice has private key alpha and Bob has his private key as beta. Both simultaneously computes alpha G and beta G and sends to each other. Then alpha B and beta A are computed simultaneously by Alice and Bob respectively. Now they both have the same key, so it can be used to verify each other and transfer data. Here are the points of cyclic group of generator point G. You can see them. Here 8G became point at infinity, so n is equal to 8 and cofactor H is nearly equals to 2. Let's have an example. You can see the values of public keys. Private key of Alice is 6 and that of Bob is 7. They compute their respective A and B and exchange them. Now Alice computes 6B, which will be equal to 1, 2 and Bob computes 7A, which will also be equal to 1, 2. Thus they verify each other and transfer data. Now let's have some talk about commercialization of our project. The new platform for programming competitions can be built on cryptocurrency. This will allow users to earn cryptocurrency by answering questions, participating in writing contests, and receiving unique badges and stickers for solving particular questions. In various online auctions, these same people will be able to trade badges and stickers for cryptocurrency. The site will be a tremendous resource for anyone who wishes to learn about cryptocurrency and programming. The site will also be helpful for people trying to develop their financial literacy. The account holder's name will be used to identify the data on the server that is required for all of these. However, the server must correctly identify it using the above mentioned method before it can be accessed. We can make money for the platform by contacting advertising agencies and asking them to post advertisements on our website. In turn, this enables us to provide our users valuable content. We can keep up the platform and keep giving everyone useful content with the money we make. Software development companies can get in touch with us to organize a hackathon if they wish to hire qualified software engineers. Developers compete in hackathons to provide the best software to solve an issue. The challenge is presented by the software development company and developers compete to produce the best solution. The winner team usually receives a prize and the software development company will observe the skill of the participating developer. Let's have a demo of the program that we have written based on this algorithm. First, we run the program at two places. First is Alice and second is Bob namely. Now, I will like to select A as 2, B as 4 and a large prime number 34039 at both the places. Now my generator point is 2, 4 at both the places. Now you can see at both the places we have different point. First you can say it is as alpha A and second is as beta B. Now write the beta B at first place and alpha A at second place. As you can see, the secret is successfully shared between Alice and Bob. So, here we conclude our presentation, and this is our team. Thank you very much.